Welcome to a new test and teardown video. This is part 2 of my Fluke 5200 Programmable AC Calibrator. Everything is now back together, fully assembled and ready for its first power up, and it's going to be super exciting for me to see where are we, what can it do. Will it explode? I assume that you have already seen part 1 and you know all about what is inside, what it does, what is this, what is the whole idea about this unit. So, what I want to do is I want to monitor both the AC voltage but also the AC frequency at the same time. So I need to use two multimeters for that. And I think that in internal sense, I think it will just measure the output voltage here, and I don't need to connect anything on this external sense. And I also hope that I don't need to connect the two reds and the two blacks. That is at least my idea. I'm not using external clock inputs, so phase lock should be in off. I am in local, and this is of course the mains power on off switch. And there is a thing that we really need to remember about this unit, and that is when you power this up, of course you should get this power on, but it will take about 30 seconds for the standby to be lit. And if that is the case, it has at least passed a little bit of voltage checks. It hasn't done that much, but if this one lights up, then we should be able to go to operate using this switch. So it's a little toggle like that. Let's see if I can do it from this view. Let's see if we can see everything. There's a long way to those LEDs over here. Maybe if I dim the light in this area, we'll be able to see what is going to happen. So here goes all or nothing. So mains is applied, and of course there's no usage, and it's using 88 watts, and I think this is very close to normal. And as we see here, we got no output. It is on purpose I set the frequency to 53 hertz. This way I know that whatever it's counting is coming from this unit and not just my mains frequency hum or anything like that. I am in 1 volt range, and see, I got the 1 and I got the decimal point here, and look what happened. I got my standby LED. So that means if I go into operate right now, it also changes to operate, and I'm happy to see that I get a little bit of AC voltage, not enough for the frequency counter here to work. So let's see if we can give it. Okay, this is not, we don't have any response. Let's go to 10 volts. But it looks like this interface here is working. That is good. We just don't get any output, and that is a little bit annoying. Maybe it has something to do with the sense or something like that, but at least I see the decimal points they're doing right. How nice is all that? 10 volts. La, 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 la. So no output, and that is where we are in the very first test. So let's see, why don't we have any output? Sense, external sense, no. This one is nothing. Remote, local. It actually did affect the output voltage. So we can go, oh, it went into standby, so we go back to operate. Oh, now I got 1.6 volts. How funny is that? So now we're in the 10 volt range and I still don't measure any frequency. Okay, output voltage is not affected by the dials, but I get 1.6 AC. That is interesting, but that is my very first little test. What is that? So to try and debug this from outside before we open and dig deeper into it, we got 3 BNC connectors at the back, and one is the phase locked. It's actually called an input. Well, I see a tiny little pulse like that, and look at the frequency counter up here, 52.6 hertz, and I got 53. And if I give this 63, look at that. So the frequency definitely something is actually responding to the frequency here. The quadratrio output is looking really, really weird, and there's nothing on the frequency counter output. So that means we definitely got something going on in the frequency system. So I don't need to worry about output amplifiers or anything like that before I got the frequencies, oscillators, and everything like that up and running first. To show the quadrature output, and it's doing the weirdest of weirdest, and we got some oscillations and some flippity flappity. I don't think it's definitely not supposed to look like that, is it? So I got a little bit deeper into this, and the purple module is the oscillator. I added a little bit of text here so I could easier move around here. So this is test point 7 of the oscillator, and look at that. And up here it says 52.6. And if I give it 10 more, look at that. I can even give it 10 more, 10 more, and so forward. So the oscillator seems to be working. Here is the status so far. Let's focus a little bit on the counter output. So this one is constantly low, and we're supposed to see some pulses. And look at that. There's a little NAND gate. Well, yeah, I'm sorry about this symbol here. This is a 7410, so it's a 3-input NAND gate, and that means if only one of them is low, there will be a high pulse. And that is the thing. We get the input from the oscillator, and this op-amp system actually works perfectly fine. So we get some nice 5-volt pulses, and those pulses trigger this one-shot timer. So we get some tiny little pulses. So we got a tiny little pulse here, and this pulse, of course, should be visible as a little pulse out here, right? And that just don't happen. I don't have a pulse on the other one, but that is because the enable, that will be of the different frequency ranges. Then this one is enabled, and this output here is blah, blah, blah. Not super important right now. But anyway, I at least get a pulse low here, and nothing here. But also, there's another one shot right here. So if this one is blown up and there's a shorted input somehow, then this could also prevent the output from going a little pulse. But normally when this is the case, you can see a tiny little pulse, but not just all the way to 5 volt. And I don't see anything like that at all. It's just constantly low. So I feel it is this one I want to replace. And here is how I normally do the debugging here. Of course, first this was just an easy point to double check. So I measured that one. This is pin 7 of this op amp. So the next stage is, of course, the outputs from this one shot, and then I put those two little wires here. I need to put in this entire board into my machine here, and then I can't just measure around here. You need a very, very special riser board for this to happen, and this is just not possible to design, really. You need to, I don't know how, they probably had one of those at Fluke in the 70s, but I don't have one of those. So that is the way I need to measure around here and figure out what is going on. And there's one more little thing I really need to put in to this little comment clip here. The counter output is, as you can see, not protected by anything at all. So an output from a TTL circuit directly drive the BNC connector on the back. There isn't any little buffer isolator, not even a series resistor. And of course it is possible to take a BNC cable to some other unit and somehow connect the inner conductor first before the chassis connection, and this way input a very high pulse voltage current spike and then blow up the inputs and the outputs of this system. So that is a big problem, and I think I will try and cut this track and put in a little resistor here, so this is not going to happen again. And as you can see, this is not just an output, it is an intermediate signal that needs to trigger this system, and the output from this one needs to trigger some other stuff that goes on and on and on. So of course a lot of stuff is not working because there's this blew up somehow, right? So here it is. This is the IC, and look at that, I cut the track and put in a little series resistor for protection, and I will perfectly fine be able to drive a cable and a frequency counter with a 100 ohm series resistor. It will actually stop a little bit of ringing at the higher frequencies, and it will in some cases protect this IC from damage. And here's the old one, 7410N, and then this is from 80. And look at that, what I find in my stock. Another 7410 from 1978, and look how new it looks. And I think I got one more move forward. So here is the quadrature output from the back, and it is a nice steady sine wave, and also the frequency counter output is actually that's the other channel I'm trying to show here, and that is the one I'm triggering on. So let's try. Here's 50 hertz. Oh well, 52 hertz. Let's dial in on the time base, and here you go, a 100 nanosecond tiny little pulse. But now it is, of course it is there, so it works, and it's nice and fine like that. I kind of like the bandwidth of this pulse, so this is a good signal quality. And so since the quadrature output is working, I do believe I'm done playing with the oscillator and the oscillator control, at least for now. So now we need to see if there's input to the output amplifier, and then why aren't we having any output? Because it still goes to operate, but I don't get any output, at least not controllable output. See, this is just the same 1.5 volt AC something, and for some funny reason I can't measure the frequency with this unit, so I will of course have to put this into my scope and all that. I just tried to avoid doing that, but for several reasons. Because if there's a weird AC-DC voltage offset and I don't know what, the output amplifier in here runs at plus minus 300 volts, so I really don't want to blow up any of my measurement equipment, at least not again. So the next step is to figure out where is the output. So let's go and look at the output amplifier. We just skip one little unit first, this AC-DC converter. This is of course for the level feedback system, but we need to get some output first before this one should be able to do anything, right? So power amplifier input, here is a little Zener diode, and that is my input. And there's a funny little coupling with a Zener diode and a capacitor here. I don't know exactly what they're trying to do with this, but this is the input. We got tons of transistors, and this is the signal path, and yada yada yada, before it becomes the output power amp. And we know this output up here is just constantly not giving us any output, right? So where is the problem along this way? And there we got a little bit of relays and a little bit of feedback this and feedback that, and some things that is really interesting in this design. So let me see if I can figure that out. But at least there is input, and the fun thing is it is a little bit phased shift. So this is the blue, that is the input. And also, of course, if I change the frequency, it works like that. So yeah, that is a little bit funny, isn't it? And here is the output from the power amplifier. So I got 4.4 volts peak, and that is 1.5 something volts RMS. And the input here is 1.5 volts peak. So there is a gain of about a little bit more than 2 times at the moment, and I believe it is in low gain mode because there is no feedback somehow, right? And it's of course not responding to anything, so this is operate, and I can hear some clickety click, and this is the output in RMS, and also this is what my scope measures, 1.5 something volts RMS. This is of course the peak I was talking about, and the blue is the output from the amplifier. So something actually do come out of the amplifier. It goes here, and all the output and relays and whatnot actually do couple this to the output, but somehow it is not responding to any kind of level feedback. So what can we do about that? I got news. See, let's try and play with the 3 ranges here. You can actually change some of the ranges and just keep it in operate. So this is the 100 volt range, and I just have it for 100. So here's my output is 15 volts. So if I take the next one, it's 1.5, and if I take the next one, it's of course 150 millivolts. So what we're looking here, the blue is the feedback from the attenuator board. There's a feedback system that goes to the AC DC converter board. That is for the level feedback system, and that input, as you can see here, is completely constant, and it's only 152 millivolts RMS. Oops, this is out of focus. Here is this feedback sense test point I was measuring at, and look at the manual. It says it's supposed to be 1.2 volts RMS, and this is of course when everything is working, and everything here is very, very low. So why is this happening? I need to of course understand a little bit what is this AC-DC converter doing and how is it controlling the amplitude feedback and all that, but at least the sense is constant. That is a good sign, but it's very low. We have, of course, this AC-DC converter. It compares the AC level from the output with the AC signal from the reference. But the AC reference is just about 1 volts, the blue one. DC, it is completely silent. So there's nothing to compare with, and that is why it's of course not regulating the amplification in the oscillator module and selecting anything really. So I think we should go and play around with the reference. Sure, I can explain this reference system in a few minutes, but it's really complex and all that. But the way that it works is there's a 10 megahertz oscillator. This works, and then we got some counters, and those counters, they are the output from these counters is mixed with some XOR gates. We got some latches and some select systems here, and that will be the switches for the different amplitudes. And of course we got this little remote switch here, and this way you can select the who is controlling the amplitude. Okay, so the amplitude, all those amplitude bits, they go to the final little output driver here. So all those pulses, they go to each side of a little transformer to pulse positive, negative, and yeah, that is at least how I think it should work. And the fun thing is the last one is a little bit different one compared to the other one. Anyway, so I took those two signals here on each side of this primary side of this pulse transformer. Now we're looking at the pulses, and I have a little trick here in the middle. I should probably just move this a little bit so it's easier to see what is going on. Anyway, let's remove the light. Can you see what is going on? We got tiny little pulses, right? So if I change the first digit, a lot happens, right? And if I change the next one, see, this is what happens. So the distance between the pulses, okay, and this is number 3 from all the way max. So this is 9 all the way down to 0. I don't think we can see the next one. So this is digit 4. Yeah, okay, you can actually see it a little bit. So, and that is, of course, the voltage dials I'm poking around with here. So the pulses to the transformer is like a PWM kind of system, right? I think I got news. I spent the whole day trying to figure out why I don't have output from the reference to the compare system in the AC-DC converter. Alright, so the missing signal here, let's go back to the reference. This is the output that is missing. It goes via this filter, and there's a little flip-flop switch, and my reference here is only 3 volts, and I measure this to this point because this point is also this coax cable. So when this coax cable is mounted, of course, that is when I have the ability to measure all those voltages. I still don't understand exactly what is the point with this resistor that just goes to negative. So now you have a little bit of current going in your ground path. Why would you do that? And then there's supposed to be a secret voltage that is called ref power supply. So this secret voltage is of course driving everything here. And there's another voltage that is 20 volts. This is also way too low. And we also got some other voltages. They are called a little F. And I think that is because they are floating. And so let's look at the power supply. There is of course a little board like this that handles quite a lot of the different voltages. This one it's also doing all this stuff, and then there is another part of it that is doing all the floating voltages for the reference board. And as you can see here, you need to measure your reference point to all this is the sense low terminal on the front. So all this is connected to the ground and la 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 la. And when I'm doing that, I get 5.1, and this should be 20. And this test point here should be 15. But it's very close to 0. And here is the ref power supply. You can see it's directly connected to 15. So now this secret voltage is finally known. There's another little thing I haven't yet figured out. The error control, and that is this fine adjust on the front. So this one actually is connected somehow to this op amp, so you can fine tune the voltages. That is weird. So the supply voltage for all those sexy reference systems and whatnot is just controlled via this little crappy op amp and some voltages from a potentiometer, and that is how it's fine adjust. Why would you put in such a nice component for the reference and then screw it up like that? It's amazing. And of course the negative side here is also not working, minus 1.8. And yeah, that is really weird, right? Both of them defective, but not quite. Because if one of them is not working, see, there's a voltage mirror that makes the negative system from the positive using those resistors here. So that is why both of them, they are not working. So let's zoom in a little bit more on the power supply. Look at this resistor here. Can you see it's broken? The one in the middle, that one is open. And this is in fact this resistor. And this is the current sense resistor. So it worked by this high voltage here, goes via this and then out. And of course if the voltage is too much over this one, it is not good, right? Then this voltage goes in here and shut it down and whatnot. But anyway, the point is, this resistor needs to be 3.9 ohm, and this is a current limit system. Why is this current limit resistor broken? It is broken because there is a short somewhere here. So the positive 15 volts is here, and when this cable here is mounted to this system, this is where you connect all the floating voltages to all the other system voltages. That is via this cable. But anyway, here's my 15 volts that is shorted. So I cannot find a short on this board, and I cannot find where is it. So what I did is I took a power supply and input just a few volts, and I don't find any current. There is no current going in the short. So I removed the power supply, and now it measures open. So there was something touching, or something was shorting, and now it is not shorting anymore. I just gave it a little bit of voltage, and I didn't see any current on my my DC supply here. I just turned it off real nice and slow, and then I have repaired the short. So now I will repair the power supply, and hopefully we will have the reference running. I got news. Hot tantalum. So they are working and they're not working. Sometimes they go hot, and they are of course running on the 15 volt system. So that is probably the problem. And this unit is just full of those, exactly the same brand. Darn it. I have changed the tantalum capacitors right here where we had this problem. But of course, if we look a little bit over here, we find 4 more. And as far as I understand, 2 of these, they are on plus minus 15 volts as well. So yeah, I bet I just change all 4 of them. So I think this calls for a new video clip. I really hate myself for not starting the video last time when we got all that smoke and stuff. So I repaired the power supply, and all the tantalum capacitors in the reference unit has been changed. And let's just do it and see what happens. It's using, damn it, 130 watts, and as you can see here, we got a lot of smoke coming from this power supply again. So the floating 15 volts is still shorted somewhere. So I bet it's going to be the never-ending story about those capacitors and something like that. Oh, how annoying. I just realized what happens when the power supply blows up and it's a positive and a negative rail, and one blows up before the other one. Then the rest of the circuits, they get a reverse voltage, because it's of course what's gonna happen, right? When we have shorted one of the rails, because now I see those filter chokes here, they light up, and they do that because the current into the opamps is of course way too high, and those are just LM301s, and they actually handle a lot of damage pretty well. But so those are, one of them, or both of them are broken, but they are of course possible to replace. But also I was looking in the back panel connection schematic, and see, this is my reference, and that will be all the floating voltages. But look at that, there's another module using the floating supplies, and that is the AC-DC converter, and that means all the op-amps here on the AC-DC converter have also been reversed. How annoying is this? And I don't find any tantalum capacitors here on the on those boards that is running on this, but the tantalum you find here, that is the other brand, and they are actually good. So I mean, I don't want to go and spend the rest of this day poking around with all those op-amps, because at the moment I just feel a little bit lost and a little bit sad and a little bit tired of this one. I think I want to put it back where I can't see it for a couple of weeks, and then I will see how to continue with this one day. But today it was not a winner, but it is a pause, and put it back on my storage for now.